Hello everyone, welcome to this lecture 27 of the NPTEL course on Riemannian geometry. So last time we started this discussion about the geometry of submanifolds. So the setup was as follows: we were only looking at hypersurfaces. So Mn comma G is a Riemannian submanifold of M tilde comma G tilde, where M tilde has one extra dimension, and this is called the ambient manifold. Okay, then the standing assumption was that M is two sided inside M tilde, which means that I can always choose a smooth unit normal vector field on M, which I will denote by nu hat. So corresponding to our choice of nu hat, we had the second fundamental form, which is essentially the covariant derivative in the ambient space, the covariant derivative of y in the direction of x projected orthogonally to the normal part. So we take the normal projection of the ambient covariant derivative of y with respect to x, and then we ended the lecture with two important theorems. One is the Weingarten theorem, which helps you calculate the second fundamental form. So it says that the second fundamental form is essentially just negative of the inner product of the derivative of the unit normal vector times y. So in other words, the second fundamental form captures how your unit normal vector is varying, and then using this one can prove the Gauss-Codazzi equation, that the curvature tensor of M is completely determined by the curvature tensor of M tilde with some correction terms coming from the second fundamental form. Okay, and at the end of the previous lecture I made this remark, which I would like to repeat because it's because of its importance, that note that H depends on your choice of the unit normal vector. There are basically just two choices of the unit normal vector. So for instance, if you have a sphere, then you can either take the outward unit normal vector or the inward unit normal vector, right. So in all cases there are basically just two choices. If you change your choice of the unit normal vector, your second fundamental form will change by a sign. However, if you look at the curvature formula, the Gauss-Codazzi equation, the second fundamental form appears in a quadratic way, right. So you multiply a term involving h with another term involving h. So even if h reverses in sign, the product of these two will remain the same in sign, which of course makes sense because the curvature is something that is intrinsic about the geometry of M. It should not depend on these extraneous choices like the choice of the unit normal vector. Okay, but it's important to keep in mind that the second fundamental form does depend on this choice. Alright, so so I would like to begin with a corollary to this theorem. Sorry. So we will now specialize to the case where your ambient manifold is simply the Euclidean space with the usual Euclidean metric. Okay, and suppose the second fundamental form is H, right. So then we have the following observation, that if you compute the curvature, now the curvature of the ambient manifold is 0 because it is the Euclidean space. So this is simply given by the second fundamental form. Okay. And as a consequence of this, suppose you take a plane spanned by these two vectors u and v. So let us say this is a plane in the tangent space at let me maybe write this down more clearly. So suppose this is a plane in the tangent space at P, then the sectional curvature of this plane is simply given by this. this divided by a similar looking term where you replace the second fundamental form with the metric. Okay. So this is a direct consequence of the Gauss-Codazzi equation. So I won't write down the proof, but let me maybe make a remark that historically the this metric was, I mean, you might be wondering, I mean, why is this called the second fundamental form? What is the first fundamental form? So historically the metric was called the first fundamental form. And especially in Gauss's time, people did not care about higher dimensional surfaces, they cared about surfaces embedded inside R3, right. So they did not care about higher dimensional manifolds. So if you restrict to the two dimensional case where you have a surface embedded inside R3, and suppose the tangent space is now two dimensional. So let us say it is spanned by these two vectors E1 and E2, then one can look at the following. One can look at the matrix of the Riemannian metric associated to this basis E1 E2. So that is basically just E1 comma E1, E1 comma E2, E2 comma E1 and E2 comma E2, and one can look at the matrix obtained by applying the second fundamental form. So H of E1 comma E1, H of E2 E1 comma E2, H of E2 comma E1 and H of E2 comma E2. Then the sectional curvature of the tangent space, because there is only one two plane, right, spanning a two dimensional vector space, namely the vector space itself. So the sectional curvature of the tangent plane is precisely given by the determinant of 2 divided by the determinant of 1. Okay, and if you recall from 2 lectures back, this is what I had called the Gauss curvature. So for two dimensional surfaces, the sectional curvature, the curvature tensor, etc., everything is determined by this one number, namely the Gauss curvature. So what this tells you is that the Gauss curvature is essentially just a quotient of two determinants, the determinant of the second fundamental form divided by the determinant of the first fundamental form. Okay, so now in order to do calculations, it is sometimes helpful to introduce this thing called as the shape operator. Okay, so this is essentially the linear transformation associated to the bilinear form, which is the second fundamental form. Okay, so more formally, the definition is as follows. So we define, for every point P, we define the shape operator as an endomorphism or a linear transformation of TPM to itself. And this is defined by the following relation, that if you apply it to any vector xp, the inner product with yp is precisely given by the second fundamental form. Okay, this is well defined because the inner product is non-degenerate. Right. So essentially what you are doing is you are in some sense you are using the metric to, I mean locally this second fundamental form is given by matrix Hij. You are basically using the Riemannian metric to raise one of the indices so that you get an endomorphism. So it is some sort of a partial sharp operator applied to this 0 2 tensor. Okay. So that is essentially what the shape operator is. So now like we had the Weingarten equation etc. for the second fundamental form, we have an analogous series of propositions for the shape operator. So firstly, SP is self adjoint, okay, that just means that SP u comma v is equal to u comma SP applied to v for all uv. Okay, this is obviously because of the symmetry of the second fundamental form. Okay, the second point is I can now rewrite the Weingarten equation for the shape operator. So if x y are vector fields on M, then in fact if you compute the shape operator on xp inner product with yp, this is the second fundamental form. By the Weingarten equation, this is given precisely by this. Right. But now because this happens for all y, by the fact that this is non-degenerate, this implies that I actually have an explicit formula for the shape operator. So this is simply given by this. Okay. So it's the shape operator is really captures the derivative of the normal of the unit normal vector. Okay, and then if n is 2, this basically means that the Gauss curvature is given precisely by the determinant of the shape operator. Okay. Alright, so again I will not prove this because these are easy consequences of what we have already done. Let me just make a remark that note that this takes values in the tangent space at M. Okay. So by 2 this will imply that the derivative of this also takes values in the tangent space at M, not the tangent space of the ambient manifold. Okay. But in fact this is easy to see. So the following is the reason why. Note that because this is a unit vector, the norm of this is identically 1. So this implies that if you take the derivative in any direction x, that is going to be 0 because it is a constant, right, nu squared is a constant. But then by the metric property this is the same as this. So this implies that this derivative is perpendicular to the unit normal vector. But now we are working with hypersurfaces, so if something is perpendicular to the unit normal vector, this forces it to belong to the complementary subspace, which is of course the tangent space of M. So this implies that this is actually an element of the tangent space. Okay. All right. So it's not surprising that this gives you another element of the tangent space of M. All right. So as I said, I won't prove this because we essentially I mean these are easy consequences of what we have already done. Let me now compute out an example. So let us calculate the curvature of the n dimensional sphere of radius r sitting inside Rn plus 1, okay, with the induced metric. So just to draw a picture, this is a picture of a sphere, let us say of radius r. Now the first point, so I want to use the Gauss-Codazzi equation to calculate this. So the first point is we need to make a choice of the normal vector. Okay, so so I'm going to take the inner normal vector. So this is just so this is of course the radial inner normal vector, which is simply this times del I, right, restricted to r equals capital R. Okay. So you basically take the radial vector field. I mean, this is just the radial vector field in Rn plus 1, you restrict it to the sphere of radius capital R. So here r of x is the usual distance from the origin. Okay, so now suppose you are given a tangent vector whose components in Rn plus 1. So let us say you are working at this point, you have a tangent vector u, its components in Rn plus 1 are given by u1 up to un plus 1, and let us say this belongs to the tangent space to the sphere. Okay, so I want to compute the shape operator. So what is the shape operator? That is just so the shape operator applied to u is just the derivative negative of the derivative of the unit normal vector in the direction of with respect to u, right. Now covariant derivatives in Rn plus 1 are basically just component wise derivatives. So you just take the component wise derivative with respect to u. So one can easily check, I mean when you take the component wise derivative, you will of course differentiate xi, the derivative of xi with respect to this vector will basically just capture the ith coordinate of that vector. So that will be ui. Okay, there is a minus sign because I am looking at the inward normal, and then ideally of course by product or quotient rule you will also differentiate r, but you are looking at a vector that is tangential to the sphere. So on the other hand r is a constant on the sphere, right, r is equal to capital R. So if you differentiate in a tangential direction, that derivative would be 0. So so for product rule you only have to differentiate the numerator and you get something like this. Okay. So this implies that the shape operator applied to u is precisely given by ui by r times del I. But of course what was u itself was ui del I, right, summed over all i's. So this is just 1 by r times u, which means that the shape operator for the sphere is simply 1 by r times the identity matrix. Okay. So that means that all the sectional curvatures are so now suppose you take so suppose you take the plane pi spanned by u and v, then it is easy to see that the sectional curvature of this plane is just going to be the determinant of the shape operator restricted to this two dimensional subspace, which is of course the determinant of the identity matrix is 1, and so this is going to be 1 by r squared. Okay, because you are going to have essentially, if you restrict the shape operator to this two dimensional subspace, this is going to be 1 by r times the 2 cross 2 identity matrix. So if you take the determinant you get 1 by r squared. Okay, so then by our discussion on how the sectional curvature determines the curvature tensor, we basically recover a formula that we proved a while back on the metric on the curvature tensor of the sphere, right, because the sectional curvature is constant 1 by r square independent of the plane pi and independent of the point. So then the curvature tensor has to be of this form. Alright, so next I want to talk a little bit about surfaces in R3, because this is historically what kick started the field of Riemannian geometry, right. So now I want to restrict to M2G contained inside a Riemannian submanifold hypersurface inside R3. Okay, so suppose I am given any So the thing that I want to describe now is how to actually calculate the Gauss curvature using curves on my surface, right. So recall that the Gauss curvature in this case is simply given by the determinant of the shape operator, right. So the idea is how do you calculate the determinant of the shape operator using curves. So let us say I fix a point P and let us say a tangent vector u at that point, and let gamma be such that gamma of 0 is P and gamma dot of 0 is this vector u, right. So again just to draw a picture, so you have your point P here and you have a tangent vector, you basically just take a curve lying in M passing through that point whose velocity vector at that point is this tangent vector u, okay. So then by the Gauss formula, if you compute the acceleration vector, so the acceleration vector is basically the covariant derivative of gamma dot inside R3. By the Gauss equation, this is going to be dt gamma dot, the intrinsic acceleration in M, plus a second fundamental form term, right. So this is the Gauss equation. Okay. All right, but note that this term being the intrinsic acceleration lies in the tangent space of M and hence is actually perpendicular to the unit normal vector, right. So that means that the second fundamental form of gamma dot comma gamma dot is precisely the acceleration vector, the component of that along the unit normal vector, okay. So in other words h of u comma u is precisely the component of the acceleration vector along this unit normal vector, okay. So that motivates the following definition. So the principal curvatures of M are defined by K min is the minimum over all such gamma as before. So K min at P over all gamma as above, of this quotient. So you take the component of the acceleration vector along the unit normal, but then you also want to normalize for the speed of gamma. Okay. Similarly, K max is the max. Okay, then the key proposition is that the Gauss curvature is given precisely by the product of these two. Okay, so this provides a great practical way of actually calculating the Gauss curvature. The proof is simple linear algebra essentially. So so note that if gamma is as above and if u is the velocity vector at 0, then Sp of u inner product with u, by definition this is just the second fundamental form applied to I mean of u comma u, but by our previous discussion this is precisely the component of the acceleration vector of gamma, the component along nu hat. So then by this what is called as the Rayleigh max min principle in linear algebra, if you look at the principal curvatures that I have defined, these are precisely the eigenvalues of the shape operator. So that is essentially the Rayleigh max min principle. So then it follows that the Gauss curvature, which we know is the determinant of Sp, is simply given by the product of these two because these are the eigenvalues. Okay. So that completes the proof of the proposition. So let me maybe end with an example. Let us now look at the cylinder sitting inside R3. So in this case let us say I am looking at the point with components with coordinates 1 0 0, right. So let me draw maybe a picture in the next page. So I have the cylinder here, and I am looking at this point P. So let us say the Cartesian coordinates are given by this. Okay, so let's say I'm looking at a point here on the cylinder with coordinates 1 0 0, right. So at this point the normal vector is basically this vector pointing in the x direction, right, or if you want the inner normal, you can take the inner normal to be minus 1 0 0. And so then the tangent space at that point is basically spanned by vectors of the form that are perpendicular to this nu hat. So they are vectors of the form 0 comma a comma b, where a and b are arbitrary real numbers, right. So now suppose you take a u that looks like this. Okay, then one can take gamma to simply be the curve cos at sin at comma bt. So one can check that gamma dot at 0 is precisely 0 comma a comma b, okay, which is u, and of course gamma of 0 is precisely this point 1 comma 0 comma 0, which is p, yeah. So now we compute the acceleration vector. So one can check that the just by simple calculus that the acceleration vector is basically given by this, okay, which means if you plug in 0 you are going to get minus a squared 0 comma 0, yeah. So that means the quotient that shows up when you try to compute the the principal curvatures. So these are this, and of course you can also find out what gamma dot is. Gamma dot is basically going to be 0 comma a comma b, right. So yeah, right, that was basically the vector u. So so the inner product of the acceleration with nu hat is basically just a squared, and the norm squared is a squared plus b squared. Clearly the max, the min principal curvature at this point is given by the minimum over all choices of a b of this quotient. So the minimum is of course going to be 0, because you can just take a to be 0. For all other values of a this is going to be non-negative. So the minimum is 0, and the maximum clearly is when b is 0, the maximum is going to be 1. So the Gauss curvature of the cylinder is 0, which is not surprising because so not surprising because in cylindrical coordinates the induced metric on the cylinder is basically just given by d theta squared plus dz squared. So clearly in the cylindrical coordinates it is obvious that this is locally isometric to R2, and R2 has 0 curvature, so this should also have 0 curvature. That is not surprising, but one can use these our submanifold theory now to calculate these curvatures. Alright, so maybe I'll stop here. So we are essentially sort of almost at the halfway stage. I thought initially that I would maybe start a discussion of the next part of the course, namely metric geometry. But since we are almost near the halfway stage, I thought we should maybe do something more fun, and so I thought for the next 3 lectures, which will take us really to the halfway point, I thought we should talk about the sum angle property, and finally now that you have learnt about curvature and so on, I thought I can finally prove the generalization of the sum angle property to arbitrary triangles on arbitrary curved surfaces. Okay, so that is namely the local Gauss-Bonnet. So that is I thought this would be a good thing to do at the halfway stage, prove our first deep result. Of course I say that it's a lot of fun, but it's also a lot of hard work. So the next 3 lectures are going to be sort of technically a bit challenging. If you want, you could sort of skip to even if you don't follow this that well, you could skip to the 31st lecture where we start the next part of the course, and then maybe revisit these 3 lectures after some time when you feel more comfortable. But anyway, that is the plan for the next 3 lectures. Alright, so I'll stop here. Thank you for your attention, and I'll see you next time around. Thanks.